Hello, you're welcome back. Okay, so we'll continue with our logic gates. All right, so now we are going to be looking at another gate and that type of gate, and that is the SOR gate. All right, now SOR gate is an abbreviation for exclusive OR gate. Exclusive OR gate. All right, of course, we already treated OR gate. Okay, now look at the symbol. Now to draw the exclusive OR gate is just very simple, just the same way you draw, okay, the OR gate. Then of course, before the input, you need to add something before the input terminal, and that's what you just see me adding here now. So this actually shows that this is exclusive OR gate. So the input is A, B, and of course the output is Y. Now by truth table, okay, the truth table of exclusive OR gates, right, is what I want to write now. So let's look at the truth table. So here we have two inputs, which of course is A and AB. Or have input A, then input B. Okay, then of course Y is my output. Okay, let's see what happens now. The same truth table we have, okay, for the OR gate, where when one input is actually 1, okay, when you add one input is 1, then when you have 0, one input is 1, okay, and the other is 0, then of course you end up having an output 1. So 0 plus 1, when A is 0 and B is 1, I have 1, and the other way around, when A is 1 and B is 0, I'll still have 1. But what actually makes it exclusive is the fact that when the two input is of the same is in the same state, okay, then definitely it will give you 0. So 0 plus, okay, 0 is exclusive SOR, okay. So of course we use this is the Boolean symbol for exclusive SOR. I will write that down, okay. Okay, so now what please pardon me, when I have 0 plus 0, I'll get 0. Then of course 1 plus 1, I will still have what? 0. So this logical addition is exclusive in the sense that when the two input is of the same state, it will end up giving you 0. So but it will only give you 1 when the two input is of a different state. So by Boolean, okay, by Boolean, this is how we represent the SOR gate. So by Boolean, Y is going to be equal to A. Now this time around, the plus is actually being placed inside a circle to show that it is actually a SOR gate, not OR gate. Alright, so please take note of that. Okay, so now let's look at other gates. Let's look at what is known as the NOR gate. NOR gate. Okay, so NOR gate is of course a combination of two words. So it simply means not or, not then or, not or. So that means it is not an OR gate, and the symbol is still gonna be the symbol of OR gate, but the output is actually being inverted. There's gonna be a bubble at the output. Please take note. Remember we talked about inverter, right? So we talked about the NOT gate. So So that means NOR gate is a combination of NOT gate and OR gate. So and that's how we represent that. The input still remain A, and of course we have the B. Output is Y. So by seeing this small bubble at the output shows that this is a NOT gate. All right. Of course, I told you that a NOT gate is a combination. You can also write a NOT gate this way. It's a combination of OR gates then at the output of the OR gate is now being inverted by passing it through a NOT gate. So what you see here is still the same. This is equivalent to this, okay, but this time around this is you are writing it in full. So that means OR gate is being actually passed through an inverter. So what does that actually mean? First of all, let's actually write the truth table for that. So we have A, then B, Y is our output. So by formula, okay, when A is 0 and B is 1, all right, definitely when you add this, all of 0 plus 1 is 1, but when you invert it, that definitely will give you 0. So invariably now by Boolean algebra, what I'm looking at is okay, the addition of two inputs after they are being added, okay, then two of them are being inverted, okay. So that is what NOR gate is all about. After you add the two input, then you now invert it. So after adding the 0 plus 1, it gives me 1, then I have to invert it to get my output. So inverse the inverted input of 1 is 0. The same thing happens when I have 1 plus 0. It gives me 1. When I invert it, is equal to 1. Okay, then I proceed. Now 1 plus 1 is still 1 when I invert it. Oh, please pardon me. This is 1 plus 1. 1 plus 0 here is 1. Then when I invert it, it's gonna be 0. 1 plus 1 is 1. When I also invert it, is 0. Okay, then the last but not the least, 0 plus 0 is 1. Okay, when I invert it now, 0 plus 0 is 0. Please pardon me. When I invert it, it becomes 1. So that is for the not OR gate or the NOR gate. All right. So now we'll look at another one, which of course is the NAND gate. So NAND gate is a combination of NOT gate and of course AND gate. The symbol still remain, okay, the symbol of AND gate, but the output is being inverted. The output is being inverted. So let the input still be A, B, and of course the output being Y. Okay, so let's look at the truth table for this. So A, B, then Y. Of course, by Boolean algebra, it's simply gonna be A dot B. Alright, then I have to invert the product, right? So what does that mean? Of course, you know very well that in in AND gate 1 plus 0, 1 times 0 is 0, okay, but when I invert it, that gives me 1. 0 times 1 is still 0. When I invert it, it gives me 1. Okay. um 0 plus 0, that gives me 0. When I invert it, that's 1. But when I have 1 plus 1 times 1, please pardon me, this times, okay, 1 times 1 gives me 1. When I invert it, that will now be 0. So that is the NAND gate. So I hope that is well understood. So now let's now go to Boolean algebra proper. Okay, so let's talk about Boolean algebra and the properties of Boolean algebra. Okay. All right. Now these are the different expressions in Boolean algebra, right? Anytime I have an input, if I add 0 to an input, a plus 0, what I will have is still the input. Okay. The same way when at the time I add 0 to any particular value, okay, nothing changes, it will still give you that. So a plus 0 is 0. That's number one expression of that we have in Boolean algebra. Now, if I add an input, okay, two input together and they're of the same state, then the output will still be, okay, one of them. Yeah. So if this is 0, 0 plus 0, you still give me 0. So if a is 0 and I add 0 to it, it still give me 0. If a is 1, I add 1 to it, it will still give me 1. So please take note of that. Now, anytime I add 1 to an input, all right, whatever that input is, all right, it will still give me 1. If the input was 1, add 1 to it, I will still have 1. If the input was 0, add 1 to it, it will still give me 1. So please take note of that. So call this equation 2, then this equation 3. Take note of this relationship, okay? Now let's look at this. We add okay, when you add an input to its inverse, or to the its inverted when you add an inverted input, okay, to itself, then you still have the input. Okay, let's say the input is 1, then I add the inverted input, okay, which of course is 0. The invert of 1, okay, is 0, right? So if I add it to 1, it's still gonna give me 1. Okay. Okay, so this is supposed to be 1. So whenever you add, when you invert an input and add it to the input, it will eventually give you 1, right? So this is so all these relationships are really very important. They are very important. Now let's look at how we are going to apply this to solve question. All right, so let's look at an expression. A is an example. Okay, it's an expression that involve the evaluation of a dot bracket open A inverse plus B. Okay, now let's evaluate this. Opening this bracket, this is gonna give me A dot A inverse, then plus A B, A dot B. Okay, so of course whenever you multiply A by its inverse, you will definitely have 0. Yes, remember, whenever you multiply opposite states, okay, when you multiply 0 times 1, definitely you will have 0. So you are only left with AB. So the final answer is going to be A dot B. All right, so there are some other Boolean algebra that we are going to be looking at, okay? Some complex question, but you need to get this basic relationship of Boolean algebra, right? So we'll look at some complex question, and that will be in the next video, right? See you in the next video. Thank you very much.